Hi everyone, welcome back. So today we'll talk about etchings, including wet etch and dry etch. So in here we can see after the photolithography, here's a PR. Then we define the area we want to do etchings. Then we start doing etchings to etch with substrate. And we'll talk more about it later. And as usual, we'll have one page for wet etch and one page for dry etch. So if you are really in rush, you can just focus on these two pages. It will have brief overview for all the important part for actions. For the wet etch, it will be liquid fast reactions, which you dip the wafer into chemical solutions. Then the product will be solubles. So here's the mechanisms. In here you create the etching species. You diffuse to a surface, you absorb it, reaction with the surface and the chemicals, dissolutions, then diffusion back to the bulk chemicals. So the etching rate, if it is generation is a key step, the etcher will be very slow. If diffusion is a key step, then the mixing will be the most important part. If a reaction is a key step, then temperature will be the most important part. So the etch rate also we can see over here first. So in here, the etchings, why we want to do etches is because this is the one we originally we have, and this is the one we got. So we'll apply the PR, then do exposure and do a develop like we say on previous lectures. Then we create the area we want to do etch. Then we can activate these films, then remove a PR to get how we want it. It is controlled by concentrations, activations energy, temperature and mixins, etc. Here's the etch rate. As we can see, here's R10 constant. And if you increase the temperature, you increase the etch rate. If you decrease the activation energies, you will increase the etch rate also. So for etchings, it has good selectivity. When we say selectivity, means that when you're doing the etchings, the etch rate for material A is lower and etch rate for material B is much more faster. This is a good selectivity. For isotropic means not only vertical etchings, you also have lateral etchings. So in here, if we decrease the temperature, we can increase the selectivities. So when we say mixing is an important part, as we can see over here. Even with the isotropic actions, if you didn't mix really well for chemicals, you will cause something like this. For the material with different chemical actions, HF can etch with silicon oxide but not silicons. So if you want to etch with silicons, you can increase add the nitric acid, which will oxidize the silicon to silicon oxide. Then HF can etch it away. For phosphoric acid, it have good selectivities. It will not etch with silicon or silicon oxide, but only silicon nitride. However, it will etch away the PR, causing the issue. So normally the mask for phosphoric acid will be like oxidize something. So that's for wet etch. For dry etch, it's gas phase reactions and the product volatile. So in here we have different type of the dry etch, and here is the gas impingement rate. So it is the gas molecule hit on the surface per minute per unit area. So in here, we got different type of dry etch, including a chemical. So it's a neutral free radicals to react with the substrate. It will be selectivities and isotropic. If you increase the voltage bias, which is ion enhancement, so not only the free radical neutral, but also ions, which will be ion bombardment, which it will be less selectivity but be more anisotropic, so you will have a better vertical sidewall. So here's another application. You apply deposits or inhibitors. Then you use ion bombardment to do the ion enhanced etch. Because the inhibitor, it will not react with the sidewall over here, but since here is all still have ions to do a physical etch, then you'll get isotropic and good selectivities etchings. Next is a physical sputtering. You just physical sputter all the materials by ions. So it will be very non-selectivity, etch away everything, but it will be anisotropic. So the dry etch controlled by gas selections. For example, if we increase the F over here, it will make the etch more faster, but will be isotropic. If we increase the carbon portion, it will decrease the etch rate, but be more anisotropic. So, for example, if we want to etch away something, normally we'll first use large F portions to etch away faster. Then we start increase the carbon portion and decrease the fluoride portions once we are very close to a target to get an isotropic sidewall. Then flow rate will also be one of the important part, and also excitation parts. And also other common cases will include SF6 or CL2. So here is the etch for the silicon. Originally, without the bias, if we increase the H2, it will decrease the etch rate. That's because H2 will react with fluoride to form HF, so that's fluoride will react with silicon. However, if we start increasing the voltage bias, we can see we will have not only the chemical etch, also will have an ion bombardment rate. So the RZ is a etch rate for the vertical one, Rx is a lateral one. So if we increase the H2 and we do a bias, then we can get really anisotropic etchings. Here is the etchings still again at CF4 with H2. We can see silicon will decrease a lot and SiO2 will remain constant. That's because H2 will react with fluoride, and the key step for the silicon etching is the fluoride with the silicon reactions. However, for silicon oxide, there's another step that is oxygen react with a product over here, and this product will mostly with carbon materials, which will form CO or CO2, which will be volatile and get away. Then you will have more chemical can come in. So it was not only rely on the fluoride reactions. That's why it remained a constant. Here's another application called DRIE. It's really similar to this one. So you etch it, you inhibitor, you deposit the inhibitor, then you keep doing the etching for ion enhance. So it will create a scattered sidewall over here. As we mentioned for phosphoric acid, if the mass is erodible, which is if this is PR not the oxide as a mask, it will erupt the mask, and which will cause, even you have an anisotropic etching, it will not still get very vertical sidewall. For sputtering, the incident angle for sputtering, it will affect the etch rate. So normally we will tilt the wafer, and we do etch. However, because a different angle, it will cause facet problems, or it will reflect on the sidewall to get a deeper etch, which is a trenching issues. Also, because you're tilting the wafers to get maximum etch rate, you will deposit on the sidewall, who will have redeposit issue cause contaminations. So that is the one page for wet etch and one page for dry etch. Then we'll start dig into the details for each of them. So for etchings, we'll have wet etch and dry etch. So the reactant for the wet etch will be liquid, for dry etch will be gas. The product will be soluble in solutions for the wet etch and volatile gas for the dry etch. So for wet etch, it will be isotropic. When we say isotropic, means that it will have verticals and also laterals etchings. So for anisotropic, it will be like more one directions, which will be like vertical one. And you will have higher selectivities. When you say higher selectivities, means that this chemical will react with a specific chemical material faster. So when we etch this, it will react with max really slow, but with film really fast. That's a high selectivities. For dry etch, will have good isotropic or anisotropic, will have good selectivity or bad selectivity, really based on what kind of method you use for etchings. So first, for a wet etch, in here, here's some mechanisms will generate the etchings, then diffusions, absorption, reactions, dissolvtions from the surface, then diffusion back to a book. So if this is a key step for generating etching species, the etch rate will be really slow. If diffusions to the wafer or back to a bulk is a key step, then mixing will be the most important part. If reaction is the most important part, then temperature will be a key step for the whole etchings. So for it was controlled by temperature, concentrations of chemicals, loss of reactive species, etch product, etch byproduct over here after etchings will block the absorptions and also reactions. Make sense of chemicals and impurity in the material, something like sulfuric acid, which will leave the impurity over here, causing the issue after the next process. So the etch rate is constant times the exponential with activation energy and temperature. If you increase the temperature, you have better etch rate. If you decrease the activation energy, you have better etch rate. So for selectivity, we can see if we decrease the temperature, we will have a better selectivity. So for mixing, it's a really important part for the etchings, because even with the isotropic etchings, if you didn't mix very well, you'll form something like this. Or if you're heating up the chemicals, the flow rate will be different. And without good mixing, you will have more etch at the side and less etch at the middle, which is how we don't want it. So this is common etch process. You apply a PR on it, you exposure it like what we say on previous lectures, then you develop a way it to define where we want to etch. Then you do etchings, then you remove PR to get what you want. So for etchings, different chemicals were used for specific material. HF will etch away silicon oxide and not silicon, so you have to add nitric acid to etch oxidize the silicon, then etch it away. You will add acetate to prevent nitric acid dissociations. You also add NH4F to keep a pH to stabilize the etch rate for HF. Phosphoric acid, it has good selectivities. It will not etch away silicon or silicon oxide, but only silicon nitride. So, also, it can be etch away the PR for the mask. That's why we use oxide to do the mask for the sulfuric acid etchings. For dry etch, as we mentioned, there have different methods to do dry etch. First is a chemical etch, which will etch with the neutral free radicals. It will be selectivities, which means it etch the substrate faster than the mask. And also it will be isotropic. We have vertical and the lateral one. If you start increase the voltage bias, you will start decrease the selectivities, because ion will be like physically etched away in this part. But it will be more anisotropic, which you will have vertical sidewall. You can also deposit an inhibitor on it. This is another application. Then you do the ion enhanced etchings, because the inhibitor over here, it will not react with the sidewall, but because you still got ions bombardment, so it will etch away this part, which will get really vertical sidewall. Physical sputtering, which you only use ions to physically sputter all chemicals, materials, then this will cause non-selectivity. It etch away everything, and it will be anisotropic. So it really depends on what method you use for the etchings. For dry etch, the chemical dry etch, the mechanism is gas absorbed on the surface, then it dissociates. So something like this, xenon fluoride, it is associate, then it reacts with the silicon, then create volatile chemicals and get away. That's for the chemical dry etch. For ion bombardment, you create the you accelerate the electrons to get the collisions, then you get more ionizations. Then you start hitting on the surface of the wafers, and you'll be more vertical, more anisotropic. So in here, you'll get more vertical sidewall. And here is a application you deposit inhibitors. Then you start doing ion bombardment. Due to inhibitor, it will now react with the chemical dry etch, but only the ion bombardment part. So it will be more vertical sidewall you can get. For dry etch, it's as we mentioned, it's a gas-phase reactions and the product volatiles, and it was controlled by gas selections. So for CXFY, if we increase the F part, we will have better etch rate but more isotropic. If you increase the common part, it will be slower but more anisotropic. So mostly first, when we're doing the etchings, we will have a larger part of fluorides to get a faster etch rate. When we are really close to our target, we'll increase the carbon part, which will reduce the etch rate, but we'll have better sidewall for a vertical one. SF6 and CO2 are others common gas for a dry etch. Fluoride will also control dry etch, as excitation part will also control dry etch. And here is a gas impingement rate. So it was defined as a molecular gas that can hit on the surface per unit area per the seconds. So pressure and temperature will be parameters for the etchings. So in here we can see we use CS4 to do etch, and Z is a lateral one, X is Z is a vertical one, and X is a lateral one. So the etch rate will increase by ion bombardment. So in here is the initial etch rate, and we start bias the voltage. We can increase the etch rate for the silicon and borosilicon oxide. So the increased part will be the vertical part. Adding H2 can control an isotropic. That's because H2 will react with fluoride to form HF and reduce the fluoride to reaction with silicon. So when it was increased to 10%, it will decrease to almost 0 for etch rate. But if you increase the bias, we can see here is due to ion bombardment, you still have some etch rate, and this will create a really anisotropic sidewall. And here's another application called DRIE. So we first do etchings, then we deposit the inhibitors, then we do etch again. And because the inhibitor, it will not etch a sidewall, but you will only etch, but you still got ion enhancement and bombardment, so you will etch down again, then you will get a scattered sidewall like this. And for DRIE deck, it's saying like the wider you can etch deeper, the narrower you will more shadow, and that's because when you do etchings, there will be the byproduct over here. For the larger one, it can goes out easily, and your etchings can come in easily. For the narrow one, it will be harder since the byproduct might be a block over here, or this is too small. The etchings will be hard to go in, so you'll get a shadow one. Sputtering, we can know that it sputtering material off the wafer physically, and the etch dependent on the incident angles, and you have those activities. And because it is dependent on incident angle, normally will tilt the wafers to maximum the sputter yield. However, there will be some issue. First is the different angle will have different etch rate, which is called the faceting, and also a reflection of a sidewall will have a deeper edge causing the trenchings. And also because you tilt the wafers, so sometimes it will deposit on the sidewall, and this will cause redepositions, which will have contaminations for the wafers. As we said, if your mask is erodables, this will cause an issue. Even with the anisotropic etch, you still not get a really vertical sidewall because you etch away the mask over here. And the next part is the etching for silicon and silicon oxide with CA4. So as we can see, if we increase the oxygen over here, it can increase the fluoride concentrations, and this is the mechanism for it. So you'll get 2F over here. So you can see in the plot, if we increase the oxygen, we can get increase for etch rate. But if we have too much oxygen, it will dilute the fluoride concentrations and eventually decrease the etch rate. That's for oxygen with the CF4. For H2 with CF4, because it will lower the fluoride concentration by producing an HF, so it will decrease the etch rate over here. And here's the silicon and silicon oxide. We can see it will decrease silicon's etch rate a lot. That's because it forming HF and no, it will reduce the fluoride react with silicon. But silicon oxide will be more constant because there's another key step for the silicon oxide is the oxygen will react with a byproduct forming CO or CO2 to get away the surface. And this is another key step for the SiO2 etchings. That's why even you increase the H2, it will not really affect the etch rate because it's not only depend on the fluoride with the silicon oxide. So you can, if you increase the H2, you can have a bad etch selectivity. And I think that's all for this etching lectures.